Hello everybody, welcome to our lesson. Today's topic is energy in a magnetic field, and this is the goal of the lesson. At the end of the lesson, you will be able to explain what is inductor and calculate the energy stored in an inductor. Well, do you remember this setup from the previous lesson? As you remember, because of using wounded wire instead of a straight wire, while switching on and off a key, this coil makes a bulb fade in instead of turning on instantly. And when the coil of wire is used in a circuit, we call it an inductor. Well, which one of these statements about inductors do you think is true? A. Inductor is a coil of wire. B. It opposes any change in current, and C. It stores energy in a magnetic field. Well, for the statements A and B you can be sure because we have discussed it in the previous lessons. As we said, inductor is just a coil of wire, and you know the property of a coil of wire. If it's included in the circuit, it opposes any change in current. And the last statement is true as well, and this is going to be the topic of this lesson. Inductors store energy in a magnetic field. In the circuit, inductors act like a resistor if there is a sudden increase in the current, and they act like a battery if there is a sudden decrease in the current. But it doesn't resist a change in current for a long time, as resistors do. After some time, inductors stop resisting and current passes through it as it passes through an ideal wire, with no resistance at all or sufficiently small resistance. So, we know that inductors act different at different situations. In general, if the current is increasing through the inductor, it acts like a resistor. It tries to stop the increasing current. And if the current is decreasing through the inductor, it acts like a battery. It tries to increase current. And after some time, if there is no change in current, and the inductor acts like a short circuit, the current, the charges passes through it with no resistance. And from the observations of the previous lesson, we know that the current in an inductor doesn't change instantaneously, and this property can be explained in forms of energy. We know from Lenz's law that induced EMF of the inductor will oppose increasing current through it. So the battery needs additional energy to push electrons compared to when there is no inductor. This additional energy is not going nowhere. It is stored in the magnetic field induced by the inductor. So in this part, while the current was increasing, the energy is storing inside the magnetic field, or we can say magnetic field was forming. And this energy will go back to the circuit if we disconnect the battery with the circuit. Well, while the current is decreasing here, the energy was decaying. It's going back to the circuit. And now let's try to find the energy stored in an inductor. To what factors does it depend? Well, we know that the work done against the inductor will be EMF times average current times delta T. So this is actually power. The voltage times current, this is power, and if we multiply it to the time interval, we get energy, work. So why we use here the average current? Because current is not constant through the inductor. It changes by time. That's why I need to use average current. And the magnitude of the induced EMF we can find by this equation, L times delta I over delta T, and we ignore here the minus sign because all we need is just a magnitude of the induced EMF. And if we put into the equation, we get this kind of expression. And here it's obvious that time delta T will be cancelled, and we have such an expression, L times delta I times I average. And if you consider that an interval of time delta T, the current increases from 0 to I, then the change in current will be I minus 0, and it's equals to I. And the average current will be equal to I plus 0 over 2, and it is I over 2. And if we put these expressions for the currents into the equation, we get this. Work is equals to L times I instead of delta I, and times I over 2 instead of I average. And we have L times I squared over 2. So this work will be transformed and stored in a magnetic field of an inductor. Well, then we can say that the energy stored in an inductor at any instant of time, it is L times I squared over 2. This is the energy stored in an inductor. And as we see from the equation, it depends only on the physical property of the inductor. We call it inductance. And it depends on the current. If you increase current twice, the energy is going to be increased by the 4 times. And if you increase the inductance also, energy is going to be increased, but with the same factor. And do you find the similarities between energy stored in an inductor and kinetic energy of an object? Energy of magnetic field and kinetic energy are analogous to each other, and velocity is similar to current. We can find the similarities because the velocity it's the motion of object, current it's the motion of charges. And here pay attention to the mass and the inductance. So in mechanics we know that the mass opposes change in velocity, and similarly inductance L opposes change in current. So well, we can say that L it's like inertia of an object. The bigger the L, the bigger the opposition to a change in current. And using the equation for the energy stored in an inductor, we can find the energy stored in any magnetic field. To do this, let's put an expression for inductance of an inductor into the equation. Well, we are going to use here as an example the solenoid. We know the inductance of the solenoid is mu0 times n squared times V, and the magnetic field at the center of the solenoid is mu0 times n times I. So if we put instead of L the expression for the inductance, and instead of the current the B over mu0 n, so we can do further operations here. We can take the brackets and square each terms here. So we see here mu0 times n squared times V times B squared over 2 over mu0 squared times n squared. And as you see, the n squared can be cancelled, and also one mu0 here also can be cancelled, and we have no mu0 at the top. So we have such an expression. Energy of a magnetic field is B squared over 2 mu0 times volume. And if we divide energy to a volume, E over V, it is B squared over 2 mu 0. And energy divided by a volume, it is density of an energy. So the density of an energy in any magnetic field is equals to B squared over 2 mu 0. Mu B, it means density of a magnetic field's energy. Well, by using this expression, we can find any amount of energy in a magnetic field. All you need is just to find what volume we are analyzing. So by multiplying this density to a volume, we get an energy. Well, this is the end of the lesson. I hope you've enjoyed our lesson. Please subscribe and share.